Uh, Today we are going to be dealing with a mouthful of terminology and a little bit more mathy type of stuff. Revisit the quadratic equation and all that sort of fun things. Those sort of fun things. But first mouthful. Second order linear homogeneous recurrence relations with constant coefficients. Okay? That's a mouthful, but we'll get into what it all means in just a minute here. A second order linear homogeneous recurrence relation with constant coefficients is a recurrence relation of the form A sub k equals capital A times A sub k minus 1 plus B times A sub k minus 2 for every integer k greater than or equal to some fixed integer, where A and B are fixed real numbers with B not equal to 0. All right. Second order means, if I'm not mistaken, it's two terms. Linear, there's no powers like a sub k minus 1 squared or a sub k minus 2 squared or anything like that. It's linear. Okay, homogeneous, the two previous terms come from the same sequence as the term you're looking for. Homogeneous means same form or same shape. Like a relational database, all the records are the same shape. It's a homogeneous database. It's a recurrence relation because it refers to other elements in the set, in the sequence, and the constant coefficients are the A and the B. A and B are fixed real numbers, and B does not equal 0. That means that the second term is required. So, state whether each of the following is a second order linear homogeneous recurrence relation with constant coefficients. A, you got two terms, so it's second order. The terms are from the same sequence as what you're trying to find, and A and B are fixed real numbers. So yes, that is a mouthful to say. Now B, there's three terms. So this would be a third order recurrence relation. So that's not a second order. C, this would be a second order because it's two terms. A and B are fixed numbers, 1/2 and negative 3/7. So yes, this is a second order linear recurrence relation. D, well, the first term is D squared, so it wouldn't be linear. So it is not a linear relation. E sub k equals 2 E sub k minus 2. Well, even though it's only one term, it does satisfy the requirements. It's just that A is equal to 0, and the first term is therefore non-existent. But B does not equal 0, so it's allowed. So yes, it is a second order. It satisfies the requirements. F, there is no second term with f of k minus 2, f sub k minus 2. So this one would not be a second order recurrence relation. G, yeah, there's A and B are just one, but it satisfies the requirements. H, the terms A and B are not constant. B is dependent on K, therefore it is not. It does not have constant coefficients. So yes, not second order, no, not linear, yes. No, it's not homogeneous. What was F again? Oh yeah, the second term was not used. So and then yes, and then no, it's non-constant coefficients. All right, come on. You were working a few minutes ago. All right, whatever. So the distinct roots case. Let A and B be real numbers. A recurrence relation of the form like we looked at in the previous few slides is satisfied by the sequence 1, t squared, t cubed, tn, etc., where t is a non-zero real number. If and only if t satisfies the equation t squared minus at minus b equals 0. That's lemma 581. All right. Given a second order linear homogeneous recurrence relation with constant coefficients, the characteristic equation of the relation is the t squared minus at minus b equals 0. Consider the recurrence relation that specifies that the kth term of the sequence equals to the sum of the k minus 1 term plus twice the k minus 2 term. I feel like I need to sneeze. Darn allergies. That is a sub k equals a sub k minus 1 plus 2a sub k minus 2 for each integer k greater than or equal to 2. Find all sequences that satisfy the relation 583 and have the form 1 t squared, t cubed, tn, where t is non-zero. By lemma 581, the relation is satisfied by a sequence if and only if t satisfies the characteristic equation t squared minus t minus 2 equals 0. Since t squared minus t minus 2 equals t minus 2 times the quantity t plus 1, the only possible values of t are 2 and minus 1. It follows that the sequences 1, 2, 2 squared, 2n, etc., and 1, minus 1 squared, minus 1 cubed, etc., are both solutions for the relation. And there are no other solutions of this form. The sequences can be rewritten simply as 2 to the n, really, and minus 1 to the n as well. Lemma 582. If the sequence R and the sequence S are sequences that satisfy the same second order linear homogeneous recurrence relation with constant coefficients, and if C and D are any real numbers, then the sequence A, defined by the formula A sub n equals C times R sub n plus d times s sub n for every integer n greater than or equal to 0 also satisfies the same recurrence relation. So consider the current recurrence relation that specifies that the kth term of the sequence equals to the sum of the k minus first term plus twice the k minus 2 term. The same as what we looked at just a little bit ago. Find a sequence that satisfies the recurrence relation, and that also satisfies the initial conditions, a sub 0 equals 1 and a sub 1 equals 8. If you recall, several sequences can satisfy the same recurrence relation, but will be different sequences based on the initial conditions. That's what we're getting here. Consider the following sequences. These both satisfy the recurrence relation, but neither satisfies the given initial conditions. But any sequence A that satisfies this explicit formula, where C and D are numbers, also satisfies the relation, just with different initial conditions. You can find C and D so that the sequence A satisfies the initial conditions specified in this example by substituting n equals 0 and n equals 1 into the equation and solving for C and D. So, substituting in, when you simplify, you obtain the system 1 equals C plus D and 8 equals 2C minus D, which can be solved in various ways. For instance, if you add the two equations, you get 9 equals 3C, and so C equals 3. Then by substituting 1 equals C plus D, you get D equals minus 2. It follows that the sequence A given by this equation for each integer n greater than or equal to 0 satisfies both the recurrence relation and the given initial conditions. Distinct roots theorem, theorem 583. Suppose the sequence A satisfies the recurrence relation given for some real numbers a and b with b not equal to 0 and every integer k greater than or equal to 2. If the characteristic equation t squared minus at minus b equals 0 has two distinct roots, r and s, then the sequence a, 0, 1, 2, etc. is given by the explicit formula a sub n equals c times r to the n plus d times s to the n, where c and d are the numbers whose values are determined by the values of a0 and a1. Example, the Fibonacci sequence f0, 1, 2, etc. satisfies the recurrence relation f of sub k equals f sub k minus 1 plus f sub k minus 2 for every integer k greater than or equal to 2, with the initial conditions f of 0 and f of 1 equal 1. Find an explicit formula for this sequence. Well, the Fibonacci sequence satisfies the first part of the hypothesis of the distinct roots theorem, since the Fibonacci relation is a second-order linear homogeneous recurrence relation with constant coefficients, a and b, both being equal to 1. To check that it satisfies the second part of the hypothesis, examine the characteristic equation t squared minus t minus 1 equals 0. Then, by the quadratic formula, t equals that mess. but the roots are distinct. So it's 1 plus the square root of 5 over 2, or 1 minus the square root of 5 over 2. Thus it follows from the distinct roots theorem that the Fibonacci sequence is given by the explicit formula here for each integer n greater than or equal to 0, where C and D are the numbers whose values are determined by the fact that f0 and f1, f sub 1 equals 1. To find C and D, you write it out, but this simplifies to 1 and 1, so it gives you C plus D equals 1, and this gives a little bit more involved. Thus the problem is to find the number C and D such that C plus D equals 1, and C times this amount and D times this amount equal 1. This may look complicated, but in fact it is just a system of two equations with two unknowns. Solving this two equation system, we get C equals 1 plus the square root of 5 over 2 times the square root of 5, and D equals minus 1 minus the quantity 1 minus the square root of 5 over 2 times the square root of 5. Substituting these values for C and D into the formula gives this. So it's pretty long and complicated, but it simplifies to this for each integer n greater than or equal to 0. Remarkably, even though the formula for f sub n involves the square root of 5, all of the values of the Fibonacci sequence are in fact integers. So there's in the calculations there's a lot of canceling out of radicals, I would imagine. But the single root case. Lemma 584. Let a and b be real numbers, and suppose the characteristic equation t squared minus at minus b equals 0 has but a single root. Then the sequences 1 r to the first, r to the second, r to the third, etc., and 0 r, 2r to the second, 3r to the third, etc. Both satisfy the recurrence relation for each given here for each integer k greater than or equal to 2. Single root theorem. Suppose the sequence A satisfies the recurrence relation given for some real numbers a and b, with b not equal to 0 for every integer k greater than or equal to 2. If the characteristic equation t squared minus at minus b equals 0 has a single root, real root, then the sequence A is given by the explicit formula a sub n equals c times r to the nth power plus d times n times r to the nth power, where c and d are real numbers whose values are determined by the values of a0 and any other known value of the sequence. Suppose the sequence b0, b1, etc. satisfies the recurrence relation b sub k equals 4b sub k minus 1 minus 4b sub k minus 2 for every integer k greater than or equal to 2, with the initial conditions. B sub 0 is 1 and B sub 1 is 3. Find an explicit formula for B, the sequence of B. This sequence satisfies part of the hypothesis of the single root theorem because it satisfies a second order linear homogeneous recurrence relation with constant coefficients, A equals 4 and B equals minus 4. And the single root condition is also met because the characteristic equation t squared minus 4t plus 4 equals 0 has just one unique root. R equals 2. It follows from the single root theorem that the sequence B is given by the explicit formula B sub n equals C times 2 to the n plus D times n times 2 to the n for every integer n greater than or equal to 0, where C and D are the real numbers whose values are determined by the fact that B0 is equal to 1 and B1 is equal to 3. To find B and C, you do some substitution and simplification, and you get C equals 1, and 2C plus 2D equals 3. And then you use that system of equations to find that C is equal to 1 and D equals 1/2. Now substitute C equals 1 and D equals 1/2 into the formula to conclude that B sub n equals 2 to the n plus 1/2 n times 2 to the n, or 2 to the n times the quantity 1 plus 2 over n for every integer n greater than 0. Okay. Like I said, there was a mouthful in the terminology and a little bit more mathy than previous lectures and all that sort of stuff. And the amazing thing is I didn't trip over my words saying that mouthful. But we'll look at the next section, finish up chapter 5. And this slide deck has an error, I think, in it. It has some stuff in it that does not make sense. I looked at it with the previous class and couldn't figure out what they were thinking on the slides. I'm thinking there's a typo somewhere in it, and don't know what they were exactly meaning. But we'll get to that in a few minutes. General recursive definitions and structural induction. Sequences of numbers are not the only objects that can be defined recursively. In this section, we discuss recursive definitions for sets and functions. We also introduce structural induction, which is a version of mathematical induction that is used to prove properties of recursively defined sets. Recursively defined sets. To find a set of objects recursively, you identify a few core objects as belonging to the set and give rules showing how to build new set elements from old ones. More formally, a recursive definition for a set consists of the following 3 components. Number 1, the base. A statement that contains certain objects belong to the set. Then your recursion rules, and it's not just necessarily one rule. There can be multiple rules in the recursion, but it's a collection of rules indicating how to form new set objects from those already known to be in the set. And then finally, there's a restriction, a statement that no objects belong to the set other than those coming from the base and the recursion. The set of Boolean expressions was introduced in section 2.4 as legal expressions involving letters from the English alphabet such as P, Q, and R, and the symbols for and, or, and not, and parentheses. To make precise which expressions are legal, the set of Boolean expressions over a general alphabet is defined recursively. The base condition, each symbol of the alphabet is a Boolean expression. The recursion rules. If P and Q are Boolean expressions, then the following are also Boolean expressions. P and Q, P or Q, not P, and P in parentheses. So there's 4 rules in the recursion section. The restriction is there are no Boolean expressions over the alphabet other than those obtained from the base and the recursion. Derive the fact that the following is a Boolean expression over the English alphabet, A, B, C, yada, 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 to X, Y, Z. And this is the expression. Okay? By 1, P, Q, and R are Boolean expressions because they're letters in the alphabet. By 1, 2A and 2C, P and Q are and not R are Boolean expressions. By 2, 2D and 2A, P and Q in parentheses and not P, not R and P are also Boolean expressions. By 3, taking the results of 3 and adding 2C and 2D, not P and Q and not R and P in parentheses are Boolean expressions as well. Finally, by 4 and 2B, not the full expression is a Boolean expression. Certain configurations of parentheses in algebraic expressions are legal, such as these two, whereas others are not, such as these. Here is a recursive definition to generate the set C of legal parentheses structures. Base, open and close parentheses, is in C. Recursion. If E is in C, so is E in parentheses. If E and F are in C, so is E and EF. Restriction. No parentheses structures are in P other than those obtained from the base and the recursion. Show that this here is a parentheses structure in C. By 1, open and close is in C. By 1 and 2A, double open and double closed is parentheses is in C. By 2, 1, and 2B, then the full expression, the full string is in C. This last statement, I don't know where it's coming from. It's kind of out of left field. But Recursion is used to give a formal definition for the set of all strings over a finite set, which we talk about later, but why it was on the previous screen, I don't know. Anyway, for the recursive definition for the set of all strings over a finite set. Let A be any finite set. Call the elements of A characters. And define the set S of all strings over A as follows. The base condition, lambda is a string in S where lambda denotes the null string and the string with no characters. The recursion rules. New strings are formed according to the following rules. If U is any string in S and if C is any character in A, then UC is a string in S, where UC is called the concatenation of U and C and is obtained by appending C on the right side of U. Recursion rule 2b. If U is any string in S, then both the concatenation of lambda and U and the concatenation of U and lambda are defined to equal U. Symbolically, lambda U equals U lambda, which equals U. Basically, if you pre-append a null string to a string or concatenate it with a null string, you get the original string. Finally, rule 2c, if U and V are any strings in S, and if C is any character in A, then the concatenation of U and V and C is defined to equal the concatenation of U and V and C. So basically, the associative property applies to concatenation of strings as well. And of course, the restriction, nothing is a string in S other than objects obtained from the base and the recursion. The base for the recursive definition of strings only indicates that one character, namely lambda, is a string. The next theorem states that each individual character in the underlying set is a string. So theorem 591, if A is a finite set and S is the set of all strings over A, then every character in A is a string in S. Suppose A is a finite set, S is the set of all strings over A, and A and B are in A. Because of the way of the definition of the string is stated, it cannot be deduced immediately that B, open parentheses, AA, close parentheses, is a string in S. To prove that this is true, first show that BA and BA in parentheses concatenated with A are strings in S, and use the fact that B concatenated with AA is equal to BA concatenated with A. So step 1, theorem 591, A and B are strings in S because both A and B are in A. By 1 and 2A, thank you. By 1 and 2A, BA is a string in S because B is in S and A is an element of A. By 2 and 2A, BA concatenated with A is a string in S because BA is an element of S, shown in step 2, and A is an element of A. By 2C, B concatenated with AA equals BA concatenated with A, because B and A are strings in S, and A is an element of A. By 3 and 4, the results of steps 3 and 4, B concatenated with AA is a string in S because it equals BA concatenated with A, which is a string in S. Proving properties about recursively defined sets. When a set has been defined recursively, a version of mathematical induction called structural induction can be used to prove that every object in the set satisfies a given property. Let S be a set that has been defined recursively, and let P of X be a property that objects in S may or may not satisfy. To prove that every object in S satisfies P of X, perform the following two steps. Show that P of A is true for each object A in the base for S. Show that for each X in S, if P of X is true, and if Y is obtained from X by applying a rule from the recursion, then P of Y is true. To perform this step, suppose that X is an arbitrarily chosen element of S for which P of X is true. This is the inductive hypothesis. And then show that if Y is obtained from X by applying a rule from the recursion of S, then P of Y is true. Conclusion: because no objects other than those obtained from the base in the recursion are contained in S, steps 1 and 2 prove that P of X is true for every object X in S. You have to excuse me, my allergy meds are wearing off. Let S be the set of all integers defined recursively as follows. Base 4 is in S. Recursion: given any integer n in S, n plus 3 is also in S. Okay, I think I see what's going on now. So it would be 4 is in S, 7 would be in S, 11 would be in S. Right? Because let's see here. So no. Fooiness. Go to try to write on the board and it screws up. All right. Where were we? Okay. So any integer n in S, which we know 4 is in S, n plus 3 is also in S. So 7 would be in S. So 7 plus 3 would also be in S. And so on and so forth. So you'd be counting by threes up to ad infinitum. No integers are in S other than those derived from the base and the recursion. Use structural induction to prove that for every integer n in S, n mod 3 equals 1. Well, first, given any integer The proof, given any integer n in S, let property P of n be the sentence n mod 3 is equal to 1. Show that P of n is true for each integer n in the base of S. The only object in the base for S is 4, and P of 4 is true because 4 mod 3 equals 1. Show that for each integer n in S, if P sub n is true, and if m is obtained from n by applying a rule from the recursion for S, then P of m is true. So suppose n is any integer in S, not any integer, it has to be in S, such that P of n is true. Then n mod 3 equals 1. This is the inductive hypothesis. The recursion for S consists of only one rule, and when the rule is applied to n, the result is n plus 3. To complete the inductive step, we must show that P of n plus 3 is true. By the inductive hypothesis, n should equal 3k plus 1 for some integer k. Okay? Because the n mod 3 equals 1, so it would be 3k plus 1 equals n. It follows that n plus 3 mod 3 equals 3k plus 1 plus 3 mod 3 by substitution, which equals 3k plus 4 mod 3 by basic algebra. And then 3k plus 1, because k plus 1 is an integer, plus 1 is mod 3, which equals 1. Yeah, 3 of k plus 1, 3 times k plus 1 is going to be divisible by 3 plus 1 mod 3 would be 1, which means that P of n plus 3 is true, as was to be shown. Because there are no integers in S other than those obtained from the base and the recursion for S, every integer n in S satisfies the equation n mod 3 equals 1. So there you go. A recursive definition can also be given for the length of a string. Definition of the length of the string. Given the set of all strings S over a finite set A, the length L of a string in S is defined as follows. Length of lambda equals 0. For every string U in S and for every character A in A, the length of UA is one more than the length of U. Symbolically, the length of UA equals the length of U plus 1, where U is an element of S and A is an element of A. The following theorem states that the length of the concatenation of two strings is the sum of the lengths of the strings. If S is the set of all strings over a finite set A, then for all strings U and V in S, the length of UV equals the length of U plus the length of V. So the additive property, that's the additive property of string length. The next theorem extends the operation of two pairs of strings. If S is the set of all strings over a finite set A and U and V are any strings in S, then UV is a string in S. The next theorem generalizes the associativity of concatenation to any three strings. If S is the set of all strings over finite set A, and U, V, and W are strings in S, then the associative property holds true for concatenation. Recursive functions. A function is said to be defined recursively, or to be a recursive function if its rule of definition refers to itself. Because of this self-reference, it is sometimes difficult to tell whether a given recursive function is well defined. Recursive functions are, of course, of great importance in the theory of computation in computer science. The following function m from an element from positive integers was defined by John McCarthy, a pioneer of theory of computation and apparently in the study of artificial intelligence as well. M of n is defined as n minus 10 if n is greater than 100, and m of n is equal to m of n plus 11 if n is greater than or is less than 100 for all positive integers n. Find m99 of 99. By repeated use of the definition of m, you do some substitution and that sort of thing, and you end up with 91. The remarkable thing about this function is that it takes the value 91 for all positive integers less than or equal to 101. Apparently this is going to be an exercise. Oh, geez. Oh, excuse me. Thank you. For n greater than 101, m of n is well defined because it equals n minus 10. In the 1920s, the German logician and mathematician Wilhelm Ackermann first defined a version of the function that now bears his name. This function is important because its values are computable but cannot be evaluated using only 4 next loops. The function is defined on the set of all pairs of non-negative integers as follows. A of 0, n equals n plus 1. A of m, 0 equals a of m minus 1, 1 for all positive integers m. And then a of m, n equals a of m minus 1, a of m minus n, or n minus 1 for all positive integers m and n. Find a1, 2. There are a lot of substitution and moving things around and all that sort of stuff. You get a of 1, 2 equals 4. The special properties of the Ackermann function are a consequence of its phenomenal rate of growth. While the values of a00 equals 1, a11 equals 3, a22 equals 7, and a33 equals 61 are not especially impressive, but a44 is approximately 2 raised to the 2 raised to the 2 raised to the 65,536th power, which is a really, really big number. And the values of a and n continue to increase with extraordinary rapidity thereafter. Consider the following attempt to define a recursive function g from positive integers greater than or equal to 1. G of n is 1 if n is 1. G of n is equal to 1 plus g of n over 2 if n is even. And g of n is equal to g of 3n minus 1 if n is odd and n is greater than 1. Is g well defined? Well, go through a few steps. Suppose g is a function. Then by definition of g of 1 is 1, g of 2, doing substitution, equals 2, g of 3 equals g of 3n minus 1, or g of 8, which is 1 plus g of 4, which is 1 plus g of 2, which equals which equals 4. G of 4 equals 1 plus g of 2 equals 1 plus 2, which equals 3. So it seems at this point to be a function. Where you run into problems is g of 5. G of 5 is g of 3n minus 1, or 14, which is 1 plus g of 7, which is 1 plus g of 3 times 7 minus 1, or g of 20, which is 1 plus g of 10, which is 1 plus g of 5, which is 3 plus g of 5, which is where we started from. Subtracting g of 5 from both sides gives us 0 equals 3, which is false. Since the supposition that g is a function leads logically to a false statement, it follows that g is not a function. And that will about wrap it up for the day. I am going to refer my first section to this video, the video for this class, because of the explanation of the problem I thought had a typo in it. But anyway, have a good day, good weekend. See you Tuesday. Don't forget, quiz, open notes as usual. Stick around after the quiz. There will be a short lecture afterwards as well. So see you next time.